Okay, why don't we get started? Welcome everybody to the fall new semester of ML+X seminars. We're virtual today, although I believe as the weeks go on here, we'll move to hybrid and then hopefully in person. We'll see how that goes. I'm Adam Clivens, and I'm thrilled to have Zoltan Nagy here kicking it off here for the ML+X seminar. Zoltan is an assistant professor in the Department of Civil, Architectural, and Environmental Engineering. He came here from ETH, right? In the Department of Architecture. Yes, beautiful place. And his research interests are in smart buildings and cities, renewable energy systems, control systems for zero emission building operations. And he's the director of the Intelligent Environments Laboratory. He's received several Best Paper awards, and I'm excited to hear this talk that's going to explain how you can use machine learning for architecture and civil engineering. So take it away.
Thank you, Adam, for the nice introduction. Thank you also for the invitation to speak here. I'm excited to share what we've been working on. I've been here at UT 4 or 5 years. 5 years. So this is something that I started here. And so I will show you where we are with that. Just a few words. What we're doing in my group is here's the fancy description, advancing science engineering, but mostly what we're interested in, my bad. Mostly what we're interested in is, talking about infrastructure in a sense that is, human responsive. So a lot about in terms of like building, occupant integration, but also, on larger scale, how do we improve society as a whole? And then also, how do we use machine learning or intelligence to do that? The more funny version to ask the question, what we're doing is basically every day, what is a smart building? Because this definition of smart in the context of building is a bit overused and not really defined. And so everybody's cooking their own soup. And so we're adding to that soup our hodgepodge a little bit and defining it as we move along. And so what I'll talk about today is one of these things, what I would consider smart environments for, smart environments and how we use machine learning for that. So my group in general basically is an application of different machine learning tools applied to the problem of, whether it is analyzing energy use patterns, which is unsupervised ways of doing it at the top left, or more supervised methods, or we're trying to fuse different techniques. On that image on the bottom left shows, extracting building profiles from images and fusing that with neural network-based building energy simulators so that you have a quick estimate of energy use. So it's kind of like a mix of remote sensing, but then also a simulator fast computation to extract energy demand of whole cities on a building level. And then bottom right, you have basically the integration of everything we do, systems, IoT devices to monitor places where we don't have data, and then integrating that with simulation models and so on. And then the topic of today's talk at the top right, RL, again, at different scales. On the human scale, building occupant interaction, how can we extract meaningful information without overburdening people by monitoring the interaction, and then applying that into the control system. And then what I will talk about today is the other one on the right hand side, which is this more urban scale energy management, microgrid type thing. And so why we're interested in that, of course, what we'll do with RL, I don't think I have to introduce it, but just in case, RL, the concept of creating a controller based on interaction with the environment. The reason why this is most intriguing for me is because you can have a model-free approach here where you don't need to know a lot about the environment. And why that is interesting in particular for buildings is because there is a whole lot of different types of buildings, and creating the environment for each of those to actually create a scalable algorithm that could be applied across many, many buildings is prohibitively expensive in my view. And so model-free approaches, or model-light approaches, I guess we could say, are much more favorable. So I'm going to a full model-free and trying to push the envelope and see where we can get. And that's kind of like just a philosophical, sort of like boundary that I put to myself at this point in time. But why we study it is the bigger picture, right? I mentioned before, we study or we try to improve humanity or our infrastructure. So it turns out a lot of our buildings are responsible for a lot of electricity that we use. In turn, this electricity has to be produced, and most of it these days is not fossil fuel free. In fact, 30 to 40% of the greenhouse gas emissions can be traced back to buildings, both in operation and also in like embodied energy that you need for building. Another 30% of our greenhouse gas emissions are due to traffic. And so that with that, 60% of our sort of like greenhouse gas emissions are directly traced back to the civil engineering profession in terms of our infrastructure and how we build and operate buildings. And the traffic, because the farther apart you are, the more you need to travel. So it's a really big problem. And so the question is, how can we contribute to move the needle towards a more zero emission environment? So what we can do, there's 3-4 things, right? This is from a recent report from the DOE when it talks more specifically about buildings. So the first thing you can do is what has been done over the years is efficiency. So doing less with, or doing more with less energy. Basically, if you look at the typical building energy use, it's basically a very minimum at night, and then it peaks in the afternoon, especially here when all your ACs go on during the heat, and then it drops again at night. And this is very, very typical, and using it more efficiently means you take that curve and it moves down, because you're mainly air conditioner. What's responsible for this load is 10% more efficient. And so you can do that a lot, but all you will do is obviously move this curve from top to down. And another thing you can do, which has been taken up quite a bit, is generate your own electricity. This is typically solar. So that means in the middle of the day, you'll get a dent in your curve, that curve that appears there. So you have a drop in the overall demand from the curve, from the grid. And then it will ramp up really quickly in the afternoon when the solar goes away. And you need to generate to meet that peak, because that coincides. So the peak load in the day and the loss of solar often coincides. So there is like a bit of a ramping issue at that point. I'll come back to ramping it later when I show you some results. And then the last thing, which is the most interesting thing, which we'll be thinking about mostly for this talk, is shedding and shifting. Shedding is not something you want to do. That's when you just drop your load. That's what happened in February. We had to disconnect from the grid a large part of our demand in buildings. Austin Energy had to. So that's something that you don't want to do usually. It is done when you have too much generation, for example, solar, and you can't use it. You're just not putting it back in the grid to avoid problems. And then shifting is something that's cool, because you can try to balance your overall demand from the grid by using some sort of storage, and then balancing out your demand, and it's more constant. And what that means is it's also more predictable, because you can kind of like coast through the day with almost a constant demand, which is nice. So that helps planning the power plant side. So that's kind of like the curve that we're looking for when I work, right? So how do we get to this blue curve, which is basically horizontal? And so the way to there is using more storage in homes and some sort of control, because if you do the same thing in every building at the same time, you'll just end up moving your peak and not, creating a more horizontal environment for like a whole neighborhood. And so that's kind of like the purpose of this talk, is to talk about this problem of storage and controlling storage, with the purpose of creating a more uniform load profile within neighborhoods. And the way, what I will talk about is how model-free RL, how we use model-free RL to do that. Again, model-free, because again, every building is different. So you don't want to have to develop and create an individual model for all of these buildings. Why we want to do that? So here's an example from earlier work. This is from postdoc work in Zurich. So here's an example of a very new building system. It's got solar thermal panels. It's got a geothermal heat pumps. So you have the heating energy comes with zero emissions. And then you have like in between the heating loops that connect all of these together. And so the idea here was, well, we already have the model in this case, so we can simulate the building, and we can explore this idea without having to go into the building and actually try it out. So you don't have to put it on the strain, but we can explore the idea in simulation. So we use the model here not for the control, but just to have the system. And so very quickly how it worked is there were 3 agents in this case. One, the solar thermal panel mass flow, one dealing with the borehole, and then the third one dealing with the space heating. They were basically not interacting because I was pretty naive back then how this whole thing would work. So we just kind of tried out what would happen. You see a little bit the rewards. I don't want to go too much into detail on this one, but the idea that you could basically, set up individual agents who you could train in a way that they would orchestrate it themselves and improve this building's operation. That was kind of like what prompted this work. And you could see we set it up and we simulated it through with real weather data for 4 years for 3 different neural network combinations for a simple, Q-learning approach. When batch Q-learning approach. And so in the first year, in the very left, you see all 3, like the green one probably by chance got pretty close to the actual like operational characteristics, which is the dashed lines. The other 3 the other 2 had some issues at the end with some bad decisions. But then, as years go by, 2, 3, 4 years, all of them outperformed and all of them performed better. And then at the end, it didn't really matter which of those would, be used. So we were not so sensitive about depending on how big that network was. And what's interesting is, when I showed this slide to folks coming from control system, they're like, yeah, but you need a year to learn. I'm like, yeah, but the building's going to stand 25 years. So a year is not a bad thing to generate at least a seasonal amount of data. Plus, we do have a year worth. You can learn from the data that you generate of your offline controller, basically. And so all in all, this proves really interesting, especially in parallel to this work. As an anecdote, the PhD student developed an MPC and trying to actually come up with like the optimal control procedure. And he achieved about the same performance as we did, a 10% increase over every year. And so that kind of like, in me, was like, okay, that's interesting. There must be more here because we did this without actually having to develop a model and at every time step or every hour come up with the optimal time horizon control problem and solve it and optimize it, having a whole like computer dedicated to just run this optimization problem. So that's kind of like where this idea for model free and exploring that comes from. So then when you put that in context, this was one building, right? So when you put that in context with many buildings and you put that in context with changing or adding smart devices to your buildings, and also that in the neighborhood, typically not every building has everything at the same time, but you have an evolution, right? Maybe you have some early adopters, like a lonely wolf somewhere in a neighborhood that has a smart thermostat. And then as years go by, more and more people get to that. You get smart fridges, you get PVs, some developer decides to put in a whole green development where everybody is connected and so on. But all of these go to the grid, right? So some sort of coordination between these is definitely necessary, right? And it just gets more as we move forward. And so the question is, right, if you all have Tesla batteries and solar power on your roofs and you all decide to store and release at the same time, you don't do anything beneficial to the grid. You just move the needle to another time. And to explore that is kind of like, or like to avoid that is where you need some sort of coordination. So we started this when I came like 2016, and we started looking into this problem of, controlling with RL, with multi-agent RL, multiple buildings, energy systems, and see what, the field it was like. You can see very few publications before 2012, 2013. And then, as you know, that was a big sort of like RL explosion in the second half of the 2010s. And so you see how also in these application of HVAC, electric vehicles, appliances, a lot of applications, a lot of papers came out, different venues. But also what we've seen is that everybody's cooking their own little soup, just like with the definition of what a smart building is. And so comparing these algorithms was extremely difficult because the problems were often different. The environments used were different. The focus of these algorithms were different, the setup, everything. So really, we did some work where we tried to do our own MARL approach, but then we stepped back and we're like, well, let's just create something where we can all compare our results for. So then we spent 2 years just to come up with sort of like an environment which we dubbed CityLearn. And the idea was to facilitate research, and so come up with a way that we can abstract out the buildings and what they do, so you don't have to worry too much about it because it's its whole own problem, and so we can focus on the control, right? So we use the gym interface for that, so that can sort of like abstract the problem and provided a way to be able to have different types of buildings with different types of systems, and then create also different types of problems. So in everything that I will show you today, we did not consider, for example, price signals, right? But it's an easy way to add that into the whole setup, just the way it was built. And it's also easy to do it every single building, a bit different for every single building.
Zoltan, I have a quick question for you. I mean,
go ahead.
If you have a building that already has like many different devices, and you're running some simple Q learning algorithm on it. I mean, if you have a city, I mean, why don't you just view that as just, a very large building with, many different devices in it and kind of run the same strategy?
Yeah, I mean, at some point, well, there's two issues, right? For one, you don't know if you're in a position where you have access to all of those devices, right? So that's a privacy thing. Like, do you connect or do you not connect? So then it's more like, what signals do you want to share between the buildings that you think were available? But you're correct. So one way to solve here this problem, or to work with this problem, is to just say, we know everything. Every building's input becomes the input to like a big, system, a big neural network or whatever, and then you try to coordinate between those. And that's exactly why we did this. So you can do that, and you can compare it to a solution where everybody's independent and nothing is being shared between the buildings. And then you can do the hybrid where you share a little bit, and I'll show an example where we share a little bit between them.
Thanks.
Does that answer your question?
Yeah.
Cool. Okay, so that's so much. So that's kind of like the framework. And again, like, it's more to be able to do all of this and not to get restricted. And then we can compare based on the loads of the buildings, which remain the same, right? So I said a lot of this already. You can abstract out the problems. You can do a centralized version. You can do a decentralized version. You can do a combine of those. So any of those, that you can cook up is possible. In essence, what you do is energy storage control. So there is 3 energy storage devices potentially in the buildings. 2 are shown here. That's chilled water and domestic hot water. Chilled water storage is not too common in homes, but you can put it in. And then the other one that is becoming more and more common, that's not shown in the figure, is electric storage that we have now in the system. It's just not shown in this figure. And what we also added since I made this slide is the option for electric vehicle charging and discharging, which is a battery with a schedule. So we have that as well on top of that. And so you can, basically pick the buildings and also pick what kind of systems are on it, and then create different environments or neighborhoods and scale it up to as many as you want. And then, yes, the idea was that you can focus on the control, and then the buildings you can keep the same, and then you can compare your results. So here's an example that I'll show. There's 9 buildings, 5 at the bottom, multifamily homes, and then the other 4 are commercial, like strip malls, offices. I think this one is like a small office or a hot dog business or something like that. A couple of them have PVs, and then all of them have storage. And so what you see as a result, so this is the average for after they're trained, maybe after 2 years, 3 years. So this is the average load profile if you don't have any control on it. So that's just what they're requesting from the grid. And you can see what I mentioned before. The average in the summer is a peak at 3 or 4 o'clock, and then the width is, the average showing the standard deviation across the whole of summer. And then the reference controller against which we compare is the one where you optimize your heat pumps and your storage to be perfectly aligned with the best COP. This is what you would do if you were alone. And this is the output of the whole neighborhood. So what you see is, again, in the summer, you would shift basically the peaks. It's a little lower, but you just get it later. In the spring and in the fall, you move the peaks. It's the same peak. And in the winter, you can actually increase the peak depending on what you're doing. So that's kind of like the problem when you don't have any control between these buildings. And so when you do have control, which is here with one of the MARL approaches that we had. Honestly, I don't remember which one it is, but you can create a control system where the response of the whole neighborhood, in this case, it's 9 buildings, is very close to that blue plot that I showed before, which is you will use a lot more in the night. So you see in the nighttime here between midnight and 6 in the morning, and also after 8 o'clock, it's using a lot more energy, but then it's relatively constant throughout the day, or comparatively constant and in this band. And that's exactly what we're looking for. It avoids these ramping problems. There is some ramping here, but it's really at high ramps for power grid, especially for gas, that you don't need to have in that case. So this was interesting. This is the approach that we used most recently last year at BuildSys, like I said, and this is the most technical slide I have. And basically all we did, and it comes back to what Adam asked, like how much can you, like, can you centralize something or not centralize something? So we found that when you have completely independent agents, you get overall you get similar behavior to the ones that the RBC. So you kind of like shift the loads, and you create peaks outside, something you don't want. We haven't experimented enough yet with reward shaping, so that's something that we're doing now. What we did here was to create a queue where agents would figure out how much they're probably going to have a load in the next time step and communicate that. And so there was sort of like a state input to every decision where we knew, or each agent knew, its position in the queue, and then the integral of all the potential load that's coming into the next time step. And so with that, you could create a lot more, coordination between those buildings, and try to shape the load that you could. And then the only way to achieve that was down here is that the buildings over time would build up their own model of their own energy use with respect to whatever they can measure. And so that's kind of like how they can forecast a little bit their use for their own sake. So you can obviously read the paper. You can look up our presentation of this if you're interested in detail, or we can talk about it more for this particular case. Here's another thing another thing that we did with that algorithm, which I like, because it goes back to what I showed you before, is that we don't have the luxury in buildings to basically, well, when you do it, model freeze, you don't have the luxury to fully train the agent before you deploy, but you kind of have to go for it, or at least that's what I would like to do. And so this example here shows like a 5-year deployment simulation of those 9 buildings. This is the aggregate for different scores, or different like grid criteria, like you see at the bottom left, ramping score. The load factor is the peak to average ratio, and then the overall electricity consumption to top right. And so what you see is, obviously in the first year, it's always chaos, because you do a lot of exploration. And then after that, you can kind of like, go into more exploitation over time, and you also know what to do. And just like in the very first example, at some point, this transition from learning offline to then, knowing what to do is interesting. And the argument that because you don't know what you're doing, you shouldn't be doing it, is not correct, because you have an RBC, or like a reference controller anyway. You can learn from that. And then once you have enough information, you can transition easily into a state where you improve a lot your performance. And so that means you can actually deploy model free in conjunction with whatever is there, best case industry standard, and then improve it on the fly by a lot. Like one is the reference controller, right? So then especially for ramping, we find very good results, regardless of the controller. Like you can see Marlisa, you can see RL2, which is just, I think, a simple RL, depending on some kind of different reward function, and then the combination. But there really is no huge difference. But the idea that you can avoid kind of like catastrophic behavior in the first year and then improve over the next years is pretty cool. So what we did then, because
Sorry, I have another question for you. I mean, given
Yeah.
that the profile, the energy profile that you're talking about, for most places, like the bands that you showed, it looks very similar depending on what the season is. Why can't you, I mean, why can't you avoid this, you know, initial, why can't you sort of pre-train or use this information that you know from these profiles to like avoid this ramp up in the first year?
No, I mean, so effectively, that's what you would do if you just avoided to use it. So I think that's more of a philosophical question. It's like, I want to see how bad it would get if you didn't do it. So then if you just randomly did it. In reality, what you can do is you do it once or a few times, and then you use that and use some sort of transfer learning to the next building, right? And then that way you can share the information. And again, it goes back to how do you formulate this problem? Do you want to be able to share that information or not? Like this is Nest data, basically, for example, like Nest thermostat, they can figure out like the thermal properties of your house, and then whether or not your AC is running and things like that, right? So basically they know everything about your home that's relevant for this. So they could easily take that information and move it to a home where they maybe don't have a Nest, but they see the signature of the AC, and then build a model off of that and then use that for control, for example. So all of those transfer learning problems that you can do, you could do. And then you probably would avoid these big peaks for every building at for every year.
Okay.
So,
thanks.
Totally agree for improvement. So when we started this, I mentioned, let me go back so I can make this story in my head. So when I mentioned benchmark problems, and so that there were no benchmarks. So in order to push this a little bit, what we did the last 2 years was to create this challenge that we called CityLearn challenge. And so we advertised heavily all around social media channels and so on to get people to use it and to basically develop, or, you know, to develop these RL controllers and push the technologies and create benchmarks. So these are the results from this year, which I got yesterday. So you're the first one to see it. We also got this year, we had monetary prizes thanks to our sponsors, including the ML Labs, thanks for that. And then the Energy Institute at UT, and then the NREL's equivalent, or the CU Boulder's equivalent of the Energy Institute, supported us. And so we can give out money prizes this year. And so you can see we score them with different grid sort of like qualities. Again, you see the load factor, the daily peak, the total peak, and also carbon emissions. We had like the conversion store, how you would score electricity to carbon emissions, because you can get it for Austin. And so you can see there's a big trend that group 1 did really well, but there is a difference. So you can get the ramping score, you can get pretty low, which is also what we found. But beyond that, you can create some nice different behaviors for this. So hopefully this will, you know, generate more and more benchmark results and things where you can compare against, because this is always the same problem and the same data set. And so that hopefully, similar to those Kaggle competitions, we can start comparing our results and creating some real progress here in that sense. You can also see that it's a really hard problem. The overall scores are always hovering around 1, which is not, which means that's a reference controller in some of these benchmark problems. I mean, you see even the best sort of like score is hovering around 1. So it is a hard problem, and that's, you know, why it's called a challenge. And so that we have that here. And then this one, this is also from yesterday, where what we did was to use some of the most advanced or the most stable baseline algorithms, state-of-the-art algorithms for MARL, which do not assume much about the environment, but we just blank shoot them on top of it. This is work with Peter Stone's group, and Bo, his student, did a great job on reworking a little bit the environment so it's suitable for input for these algorithms. And you can see it's not an easy problem also for these. So this is state-of-the-art RL on this problem. So we have some work to do. You can see on ramping, some of the algorithms do pretty well, others really not so well. And then, on the total score, which is kind of like the average, we're hovering around 1. And so, there's a lot to do and interesting problems to be tackled, and see where we can explore, advantages of this algorithms. What happens, this is 9 buildings. What happens when we go to like 100 buildings? How does that compare? Can we pull out more, advantages? Do we need a certain threshold for the amount of storage that we have in the neighborhood that we can create some response? And so this all goes to what, if you have seen the DOE's announcement on grid interactive energy efficient buildings, this is kind of like the idea that you create a link between the buildings and the grid and have the buildings being an asset for the grid, but it also requires to do it in a certain way. And so that's kind of like a contribution to that, direction of work that's coming more and more now due to climate change. Some, success stories, like I said, we have 2 rounds of the challenge now completed. We use this also as a teaching tool to introduce RL specifically for power systems. It's been used also at UT as in Peter's RL class 2 years ago as like a potential for a student project. What's very exciting is with some colleagues at Boulder, we're creating a grid interface to this. So we create where we can do voltage control. If you had like smart inverters and you want to make sure that you're stabilizing the voltage or not destabilizing the voltage. So on top of the energy demand, you also want to make sure that you keep your voltage, in check. So it creates a link between the thermal systems and the electrical systems in the building, which will be more and more important when we talk about electrification of the buildings and more self-use. And then, of course, like I mentioned, people starting to use CityLearn. So there was some works that did just what I mentioned before. What if you had one omniscient agent that knows everything and then tries to organize it, and then you can compare that to, what if the agents are all individual and don't talk to each other? So this is all kind of interesting. It's all on GitHub. You can go and download it. It's all free. That's in that sense. Take a look. And then if you're interested in these topics, I'm also organizing this community workshop at BuildSys. Last year we had the first edition. This very specific topic of using RL or similar for energy management in buildings or larger scale, trying to work out the kinks, the big pictures, comparing notes. It's coming, but we usually have like 1 or 2 papers in BuildSys. So this event last year, we had a few more, like the whole afternoon was quite interesting. This year we'll have another session. Still time to submit a paper, but until Monday, if you have something in the cooks. Other than that, you're welcome to join. It will be online. It will be streamed probably again because, well, COVID. Otherwise, it will be Portugal, but it's happening. So probably again, last year we had like 100 people throughout the whole afternoon. Quite interesting. And again, good conversations on this very, very specific topic and working out like small questions, which is quite fascinating. Okay, I think, yeah, there's more. You can, our YouTube channel is full with RLM papers and those short videos if you're interested in what's going on. A lot of work is being done in the national labs, LBNL, NREL, and PNNL. We're trying to create this link between the control systems and the buildings and how that works between the different energy systems. So it's very exciting times for this place, I think. And with that, I think I'm in time. So we have time for conversation, discussion, and I'm happy to take questions.
Great, thank you. Yeah, that was a great talk. Thanks. We have time for some discussion if anybody wanted to ask a question. I mean, I guess the big question is sort of what are the prospects of actually, getting Texas to deploy some of these systems to avoid another sort of snowpocalypse.
Snowpocalypse.
Yeah. I mean, is that in the works, or is it too disjointed to even attempt something?
No, it's a great question, and I guess my work this work became very relevant very quickly in the last half year. But there's a few things. So I talked a lot about building scale deployment. There is the mid-level here where there's utility scale. So where a utility itself owns a large amount of battery, and that's coming more and more. You probably
And there you have an actor who actually knows everything and can control everything.
or knows more, correct?
Knows
so
more, yeah.
Yeah, correct. So and you would shift more, according to the whole grid, and then you can have a bigger impact on that. So definitely that is an opportunity to explore it more. California has a lot of storage. I'm sure you have seen the Tesla news. Tesla is building a ton of batteries. Also big test around, I think, Houston, again, grid scale or utility scale battery. So that's probably something that will happen very soon, to offset some of those issues that happened and some of those peaks that we get. Another thing that can happen with this is there is an opportunity in Texas, because of the way the market is regulated or not regulated, is there is an opportunity for like an aggregator. Like, so basically somebody who is not a utility and who's not yourself, sitting between you and making sure you get your energy, but making sure you get the best deal while you're shifting the load and providing a utility with a flexible load. So the whole conversation currently is the value of buildings in flexible loads or providing flexibility. Right now, there is no consensus of what that necessarily means. How do you measure flexibility? We're developing KPIs and things like that right now. And so slowly but steadily, we get to there. Currently, there are a few bad examples, like you've seen the ones in around Houston area that basically just transmit the price, the wholesale price to you. That's not what should happen, because then all of a sudden, some people got like thousands of dollar bills. That's what you want to avoid. So this is why there is a risk. The utilities don't want you to deal with this because they don't want you to mess with the energy system. It's unpredictable, right? So Austin Energy does not want you to have a lot of storage necessarily or a lot of solar, right? But that's something you can decide if you wanted to do. What they want to do, they want to be in charge to make sure that everything is stable, everything's secure, and everybody gets the thing. But that means that they have to deploy their own storage. And so what I think will happen is, because it's Texas, you get probably nice solutions, different types in many places. There are companies that do this aggregation. There are some nice works out in Whisper Valley where there is a community that shares a thermal grid with chilled water. And there is a company that's managing that thermal grid. And with that, all the loads in those buildings and interfaces with the utility. And so they provide you safety to utility of not having to deal with consumers who are not happy, but then providing the benefit to the consumers of always having the cheapest price. So that's the kind of things that will probably pop up a lot.
Does renewable energy certificates factor into play here?
Well, I mean,
you're gonna have a lot of people who just want to make money off of the electricity that they're generating.
Yeah, so I think that will be a factor. If there is I mean, like you said, I have not been here a long time, but the feeling I get is if there is possibility to make money in Texas off electricity somehow, it will be made somewhere, right? It's a big enough place, and it's splintered enough that will happen. But what we've seen though over the last year very clearly is that a lot of people also just want reliability and resilience, right? So do you want to maybe a system that if your power goes out stays on, or do you want to keep having your generator in the garden? Like, that's kind of like the question that people make a decision of, right? So right now, it's not, you probably will never get, or it will take you quite a bit to actually get a, like a payback for a system is still pretty long. And so people who buy now don't really care about payback. They care about, I don't want my power to go out for 3 days again.
Right.
So, and how do you price that, right? So that's a different price, I think. Yeah. So I think we'll see more of those, and then that might drive the price overall down. And then we'll see things where, I mean, right now, Austin Energy can control your thermostat, right?
Right.
But but then the Tesla is deploying batteries that can be controlled also by the utility. So probably that is the next step, as like immediate step in places like here where a lot of those are expected. And then if you have your Tesla in the garage, that's also battery. So that's an ultimate next step, right? That's a big battery.
Right.
Makes the problem harder.
Can you talk a little bit about, how you're using deep learning, I mean, to build some of these models? It seems like, you already have sort of a handle on what peak usage looks like depending on the season. So what are you actually predicting there?
Yes, so I think it's not on this set of slides, but essentially the inputs to these models are environmental inputs. So some of those are current insolation, current temperature. Some of it has like an idea of the forecast. So because we know everything, we can say we know with a certain probability, like some noise, what the future forecast will be on the insolation or temperature. We know the state of charge of the batteries, of course, and things like that, and temperature, humidity. What we don't use is we don't really deal with like scheduling dishwashers and stuff like that, because it's not necessary. But overall, the state space for each building is, I think, 10 or 12 variables hourly, and then that's kind of like what we're using. It's not something that you would not be able to have in general. In a general problem.
Okay, so you don't have thousands of features. You can train them, with not too much data.
No. It's 10 features, or 10 or 12 inputs to the algorithm. We did some testing, like how big these neural networks have to be, like the size of the layers in between, and how many layers you have. And so we just kind of like, what I showed you was the latest of those. It varies also a little bit by area. So if you take the same problem and move them to Colorado, you get different set of results. You might get better results. If you move them to Chicago, you get a different results or better results, right? So in a place like here, it's which is the result I showed you. It's a hard problem because you cool all the time.
Right.
So
right.
so
right.
so there is, like the shifting happens for pre-cooling a building is typically what you want to do, and that's kind of like what you learn, and then you try to do it separated for all the buildings. But a place like it's a little bit more temperate, California, Northern California, maybe Colorado, you have a lot more leverage for these. So that might be another thing that drives these application for these, is where it works better. But
Anybody else have a? Oh, sorry, go ahead.
No, the state space is pretty small, and the action spaces have 3 variables, right? Like
right.
Charts.
Gotcha. Anyone else have a question?
I have a question. This might be like a wacky question, so if it is, I'm perfectly okay with you telling me it's ridiculous. But are the inputs, could any of the inputs be based upon sort of economic factors? And then I just came into here kind of seeing it for the first time, so I'm not really sure what the optimization is, but and then optimize for cost, something like that.
Yeah, I mean, so what you can do is, or what many people do, and when I showed the review in the beginning, what many people do is they say, assuming a certain cost structure for electricity, the optimal or the objective of our controller is to minimize the cost for the user, right? And that's how it's been done for years, and we could have done that. There's 2 problems with that I mean I see is that's not what we want to do, because it will just emphasize the status quo of the problem, which is you have a peak time and the load, like an off-peak time, and that will result in basically those 2 peaks that you've seen from the RBC controller. And also because ultimately what we want is for the benefit of society, if you put it this way, right? Not necessarily cost reduction for the user at this point, but making sure we can have a renewable energy across the day, which is what you get when you can lower the peak and distribute what you generate throughout the day. So, but it is straightforward to add a price signal to this, right? So we just haven't done it. You can experiment with creating a price signal that says, for the next hour, we're forecasting, increase in price, and then you can learn how to react to that. And that's a typical demand response, what you would have today.
Or
retail
like,
market.
still keep the same optimization, but just have various economic factors in the inputs. In other words, you could still, go for the more altruistic goal, but, just find out, are there some things in the inputs that could kind of be on the more sensor data type of thing?
Yep.
That's just a thought, just a wacky thought.
Well, it's really wacky now. But what is interesting is, another reason why it's challenging to do it, or at least the results that you get are a little bit different, is if you get many people to shift their loads, your price structure is not correct anymore for the utility, right? So you basically can create a different market, and that's again where sort of like a middle aggregator would be interesting, or could exploit certain inefficiencies in the market, or you can create a new market. Like that's kind of like the ideas that we can explore now. We just haven't touched it yet. There are some people who do RL controllers for bidding. I think even Siemens has a call out right now to sort of like create control systems that can optimize their bidding strategy if you have dynamic pricing in the grid. And that's definitely an interesting application.
Yeah, interesting. Thank you.
Cool.
All right, if we don't have any other questions, thank you so much for a great talk. And this is obviously an exciting and interesting area. And we'll keep in touch.
Thank you. And feel free to get in touch if you're not speaking up. I'm happy to have one-on-ones and so on. Thank you.
Thanks again.